interest from Paderborn, and she's going to tell us about the cluster character map for the derived category of the text algorithm.
Thank you so much. Thank you to the organizers for the invitation to be here. And really nice to be around old and new faces. So I'm telling you about some very much still ongoing joint work with this team from WinArt. Yeah, so anyway, we know that I'm not lying, but we know the things, we know the theorems, but it's ongoing work. So if anyone has like suggestions or whatever, we extra appreciate it. Like for further things we do. Anyway, I want to start with some motivation. A lot of things I'll say at the beginning have been touched on before, but I think I won't be too repetitive. So our motivation comes from triangulations. Okay. So from a triangulation, abbreviated, E of a unpunctured surface, you can build two algebras. Okay, so let's draw a triangulation. One, two, three, four. So first, a lot like in Karen's talk, we can build a, or just like in Karen's talk, we can build a gentle algebra. I guess we just learned all about this, but let's just recall. So we're going to have a quiver, a directed graph. So the vertices correspond to the arcs in P. And the arrows correspond to the angles. So in this case, it would look like this. And then the relations. So in this case, since it's from a triangulation, it's actually almost easier. So you either have like here 1, 2, 3 is an internal triangle. All three sides are arcs for my triangulation. So I take every composition of length 2 for my relations. And my other triangles have at least one end on the boundary, so they don't contribute relations. So it's like an easier version. But we just forget about it. Here these. Okay, you can check that this is indeed a gentle algebra. And in fact, it's also what's called a Jacobian algebra. So it has many nice properties. That's algebra A, and then algebra B that we can build from this, which has also been briefly mentioned, would be a cluster algebra. Okay, and then people like to dubiously talk about cluster algebras and not define them, and I'll do the same. But the idea you should have in mind for the general definition. Okay, and then I have the same quiver here, but the relations aren't shown. So here I have a cluster algebra of rank 4, right? 4 arcs my triangulation. I should think about some data labeling 4 regular graphs. So here I have some initial data coming from this triangulation. And then in the theory of cluster algebras, you always have a way to take any of your 4, this data is a collection of functions, like algebraically independent functions, and some combinatorial data, which here is just a quiver. And I have a way to remove one of my functions and replace it with a new function so that they're all still algebraically independent and form a transcendence basis of the thing you're working over, blah, blah, blah. So for example, here, I guess I'll say slightly more details. So for example, how could I replace x1? So I'm going to draw a line between these and label it 1. Well, in 1, I would look, I see 3 there. 3 pointing into 1 and 1 pointing out to 2, and there's nothing else going on near 1. So I replace x1 with this new function. And then I have a new quiver here. And it turns out this new quiver you could also read off, you could also construct by flipping the arc 1 in the triangulation, so removing 1 and putting in the unique other arc that makes the resulting thing a triangulation. Yes, okay. And so again, you should picture some four-regular graph where everything is, you have line, every vertex sees lines with labels 1, 2, 3, 4. And you're doing this replacement game in all of them. And sometimes maybe they coincide, but there's no guarantee of it. Oh, so two very different algebras that I can build from this data. I guess it's really not clear how that has to do with the triangulation. But there's really nice kind of properties between these. Okay, so both of them came from, anyway, both of these come from the triangulation. And we have dictionaries between simple arcs in S and M. So on the one hand, they correspond to rigid indecomposable modules of the gentle algebra. I guess to say this, I should say they're not in the triangulation, but this is only the motivation, so maybe I'll slightly lie. But anyway, in general, simple arcs correspond to like really nice modules. On the other hand, for the cluster algebra, okay, so a priori, you have to think about a four-regular tree, which is like really big and overwhelming. But actually, all of these functions that show up, which we call cluster variables, we could index these also with simple arcs in the triangulation. So cluster variables, which is incredibly useful. Like in general, for cluster algebras, there's not nice ways to index them, and it makes it sometimes hard to study. Okay, and then we can bypass the simple arcs and go directly from here to here using this cluster character / Calder-Champetone. And something that I really like here, so yeah, and this map has been discussed a little bit. Oh yeah, maybe I'll do an example. I won't give the definition, but when you look at this map the right way, it also looks a lot like some of the combinatorics that you can use here to go from arcs to cluster variables. So you can prove this. Anyway, there's various ways to prove going between here and here, but one uses this machinery called the state graph, which is really fun. You can boil everything down to looking at perfect matchings of these fairly simple graphs. And then the Calder-Champetone map, it kind of looks like the same graph mapping. So many different worlds tied together here. Let's see, let's do a quick example. Just so you can see what the players are a little bit. So, okay. Here's an arc on here. So let's call this gamma. So I promised you this should correspond to a module and a cluster variable. And we also learned that think about modules, we can just think about quiver representation, meaning I can label my quiver with like linear. So this crossed lines 1 and 3 and nothing else. So I will draw a one-dimensional vector space K at vertices 1 and 3, zeros elsewhere. I have I have some non-zero map between these, so it might as well be the identity. And then, well, this is the only reasonable way to label the rest of the arrows is with zeros. Okay, so this would be on the side, and then the cluster variable would be, I can do math on the spot, it's very scary. X1 would be 4 plus 2. Let's see. Oh, I see. Oh. And so then the CC map takes you from here to here. And okay, if you like combinatorics, you like think about things like order ideals. I can picture this as like a chain of length 2, and there's 3 order ideals of chain of length 2, and then I can picture the 3 transfers. Those are great. Anyway, again, this is our motivation. This is a nice story. I'll point out one consequence of this. So on this side, the simple arcs, the cluster variables, you can talk about this both combinatorially and geometrically. You can realize cluster variables as Penner's lambda links. So a consequence of this beautiful story is that in this setting, the CC functions, these outputs of the map, they satisfy scaling relations. Meaning, okay, when I talk about a scaling relation, I'm meaning if I have two arcs that cross, they have corresponding modules, corresponding color functions. And I can think about the two ways to resolve that intersection, and I get, other CC functions, and the CC functions represent or respect this diagram. Okay, because that was some of our motivation. We were like, so basically our project was hunting for something like a CC function that would do this in a big set. Any questions on this? Or I guess, okay, this is just the background. Okay, so the natural thing to try, so there are many gentle algebras that don't come from triangulations. We learned they come from tilings or partial relations. So we started our project with thinking about how could this story extend to that setting. So in that setting, we'd have, we still have simple arcs. Okay, we still have arcs going to modules, but there's not like a clear like cluster algebra. So we're like, oh, could we cook up some algebra that acts like a cluster algebra for that? So our first is so for an example of a gentle algebra that's not also Jacobian, not coming from a triangulation. So this looks similar. But then I move some things around. And then here's the geometric model. So we've just learned the geometric model for these is by Bauer. Samoas. Oh, so our geometric model for this will again be an annulus. Let's see. We'll again have an internal triangle because we have this kind of complete triangle of relations. But now so arcs 2, 4, 3, we have one face that's a fourgon. Okay, so it's just like a little bit non-triangulation. One face is not. Yes. So when you're working with things that aren't, so triangulations are incredibly nice because anytime you enter a face, so if you enter like a triangle, you're going to leave by one of the other two sides, and there's always like this like unique mark point you kind of cut off from the rest of the face. And so much common for arcs just comes down to like, look at that mark point. Is it to the left of your path of travel or the right? It makes things really easy, kind of one-dimensional. But when you have faces that aren't triangles, you start having to like decide what you're going to do about them. And we saw like here they introduced the idea of permissible arcs. So an example of an arc that isn't permissible would be like, oh, sorry, I'm missing some mark points. Just to kind of make this non-degenerate. Okay, so this would be like a bad arc here, a non-permissible arc. Okay, and anyway, so this doesn't correspond to anything because it would correspond to going through a relation. It just kind of has to be there. But we wanted to be close to the cluster story, and we wanted something where we want to take arcs and just kind of naively do scheme relations, and it's sort of too restrictive here. So I'm telling you why we didn't just look at the model category for arbitrary gentle algebras. I'll also mention that one of our collaborators, Azura, she did give multiplication formulas for CC functions for general gentle algebras. And they don't always quite look like that. Sometimes you need some extra variables up front. So anyway, these are two reasons why we put this aside and actually look at the derived categories. Okay. That's gonna be my running example. So maybe I'm gonna draw it like here. Okay, so now we're gonna, instead of looking at modules, we're gonna work over the bound-derived category of these gentle algebras. Which maybe sounds scary, honestly, sometimes it's scary to me, but we can, in this setting with gentle algebras, everything can be boiled down in a pretty concrete way. So our objects now, instead of looking at modules, we're gonna be looking at like complexes of projectives. And thankfully, when we're working with like these bound quiver algebras, that also we can boil down in a pretty in a concrete way. Okay, so let's recall, so there's, in this setting, there's one projective module for every vertex. So we call it PI for every vertex I. Okay, and the complexes, we have maps between projectives and name these. Where else? And maps between projectives come from non-zero paths. When I say non-zero, I mean I don't go through a prediction, right? So my ideal, I'm quotienting this path algebra just by a monomial ideal, so I can just think about paths that don't go through those forbidden paths. So a non-zero path I to j, I call it P, gives a map going the other way from P to j. Okay. So it's sort of like the strings we heard about last talk, a little different, but I don't mean slightly different, but yeah. So an example, the sort of thing we're going to look at here. So we could have, let's start with P2. Okay, and P2 has, 1 goes into 2 and 4 goes into 2. So reverse, I can map P2 to 1 and from P2 to P1 and from P4. Okay, and then, well, I can choose to not do anything with P1, and then from P4, so P2 goes to P4 with BE. So then, right, B2. Okay, and since E and D is a relation, this is a complex, like when I compose them, I guess. And what people like to do sometimes, so is what's called, they like to unfold this. Right, because the P1, this P1 was interacting with the P2. So I could just draw something where arrows are going both ways. And again, it makes everything somewhat one dimensional. People like to unfold them. But then when you unfold it, you just kind of read, you can read the paths across. And you just get, again, some word in the arrows. Well, arrows and inverse arrows, arrows of the quiver, because the arrows of this unfolded diagram are going both ways. So this is called a homotopy string. Okay, going backwards, I could know that from this string, I should write this diagram, because between A inverse and D, I'm switching whether I have an inverse or a non-inverse. So that's how I know I kind of have this P2 with both things pointing out. And ED is a relation here, so I'd also know degree. Okay, so everything can be boiled down into these words. What next? Any questions right now? Oh. This doesn't move. Oh, it does. Hold on, I thought it did. Maybe your choice makes sense. Okay. Great. Okay, and then there's also so we heard a lot about geometric models for module categories, and the setting of the bounded derived category of a Structural algebra also has a geometric model. I don't want to oversimplify it because there's also I'm hiding everything, like these are complex ways, like everything lives in some degree, and I'm just hiding all of that because it's technical and not, I don't think it adds to understanding. But all that to say, the geometric model here for the same algebra, but it's not a direct category, we can see is like the dual dissection, the dual tiling for this. Okay, so I'm going to replace faces with vertices with faces, and then edges crossing. This geometric model is being given by offered and control. Okay. So this corresponds to 4. You notice, like, if I drew this on top of that, it'd be, right, some sort of dual graph. 1. Okay, then I'll draw a second set of mark points. Open circles. Like that. Okay.
What is the end of one? Black?
Yeah.
And then on the bottom.
These are black. For here, I guess there's so many colors here. Let me just use color. Okay. Okay, so again, I have, well, yeah, we'll unpack this, but to start, I have 4 arcs here. That's good.
There was a false end of one.
Yeah, top of one.
Oh, I'm sorry. Yeah. That's okay. Thank you. Okay, so again, we have vertices, arcs in the partial triangulation. Arrows go to angles. In fact, it's possibly useful to label that. So I'm going to label it here. Angles between 2 things in my dissection. I'm ignoring the boundary. But since I guess this is probably expected because it's a dual, notice it the way that we see relations is dual to the form. So maximal paths, or just paths, I guess, correspond to faces. Like, let's see, what's a path? Like BE is a valid path, and I see B and E lying in the same face. Whereas relations correspond to fans. So this is opposite of. Let's see, what's the relation? AC is a relation, right? Yes, AC is a relation, and there's a little fan. Okay. So the so on top of there's finite homotopy strings, there's infinite, there's bands. I'm only going to talk about the finites. So the finite homotopy strings correspond to set up good notation, arcs with on these yellow points that I draw. Okay. So our example there would be this. Okay, because what was there? So it's, let's see. So okay, forget this one. Okay, so I start, I'm in the first space, nothing counts in the first space, you're just getting started. And then I go through the space, and I see A, let's say minus one. I see A to my left, and it's like I'm separating A from the unique yellow point here. So again, every face has a unique yellow point. So the game is which angles am I separating from that unique point? So in this stretch, I'm separating A from the unique yellow point. So this part collects A. Then on this stretch, I'm separating D from the unique yellow point. So I pick up D. So it goes A inverse, or A inverse D, and then here on this stretch, this long stretch, I'm separating E and B from the other point, so I can pick up E. Okay? So that's the game here. Now, morphisms correspond to intersections. Having recommended, but I'll draw another arc here. But this one will be really simple. Actually, it will be simple. Okay, here's another arc. So these intersect. So we're gonna like kind of, this is our running example. So that means there's going to be a morphism between the associated objects in the category. And you actually need to keep track of like readings and things like this, but these are all the details I'm paying. Okay, so morphisms correspond to intersections. And our whole, we're really motivated by these scan relations since it's quite fundamental on the cluster side that we're trying to emulate. And thankfully, the resolution of an intersection encodes the map, which is similar to looking at like a lot of people have spoken about X in the middle term. So this is what. Yeah. Okay, so let's look at this example some more. Are there any questions while I read? Okay, so we have an intersection. And actually, when we have so intersections include on the boundary, and those kind of only go one way, but these internal intersections, you'll get morphisms both ways. For one, you need to like shift one of the complexes. So we get a pair of morphisms, which is good because when you resolve intersections like geometrically, you get. So we'll see two morphisms from this intersection. So the first, so we can go from P purple to P red. So, okay, so P purple, this new thing I drew, it's quite small. It only is cutting out, so it has a first space that doesn't give you anything. Here, it fits really close to E. It separates E from the other point. And then here, so P purple is just this. Okay, that's all. Pretty small. And then P red, as we've done for. Wow. Okay, so we have, when these are in the same degree, we have a morphism where this is like an identity morphism. And here again, I have a morphism from 3 to 2 because there's the arc B from 2 to 3. Sorry, here. Okay, so this is a morphism in the category. And it's mapping cone. So there's this lovely classification of the mapping cones by Donati, Pastel, and Scholl. They show these really nice diagrams, how you can just sort of circle what the mapping cones will be. You don't have to think too hard, which I was usually. Oh, let's see. Trying to circle this with a different color. Okay, and then I promise this should correspond to some sort of resolution. So maybe. Okay. So this corresponds to the resolution. This. And this one is harder to see because this comes from resolving this intersection like this way and you pull things back. So if you're not quick with this, it might be harder, but the other one's actually easier. So here's one. So map going that way, we have this mapping cone. And it's what's one thing you would, one of the terms of the geometric simulation, and then there's another going the other way. P red. goes to P purple. I'm flipping this so that the drawing is nice. This map is this. And then so here your mapping cone is this. And this corresponds to the other way you can resolve that intersection. Namely, this. Okay, these still cross because one of the arcs we started with has some, but notice there's like less. Okay. So that's that story. So okay, the point is there's this geometric model of this cell. Things feel a little more complicated, but many of the same, like the same features are going through. And in particular, you don't have to worry about permissible arcs here. I guess everything's just kind of bigger. So we're back to where we can kind of naively think about things crossing and resolve them, and hope to come up with some formulas that respect these things. That's it. All right, so now I'll give you our construction. We're going to mostly just, I'm going to give it by example of this running example. So our variables, so we're going to be working with Laurent polynomials in the following variable set. We'll have one variable for every vertex. Okay, so Q0 is like vertices. And we'll have one variable for every arrow. You shouldn't think about these like y variables in cluster algebra. It's just the next letter after x. And then we'll also have a parameter q, which has to do with the fact that these are, everything's in some degree. So this keeps track of that, but of course I have hardly been talking about that, and I will continue on to not really talk about that. Like how it relates in the q's explicitly. Now from this diagram, I'm going to unfold this a little more. Sorry to have that low. Okay, I'm going to briefly unfold my unfolded diagram even more. So you can look at this while I define some of these things. So in each of these stretches, and again, I'm just kind of bending the path when it corresponds to an arrow. So also don't think about this like a poset. So sometimes people call each of these like a letter, the homotopy string, right? A little string, those of letters. So I have letter 1, letter 2, then EB is one letter altogether. So we'll have letter polynomials. So this is letter 1, so we'll have this one will have YA. This one will have, so the first two are boring because it's like a single arrow from the quiver. So YA for the A, YB for the D. But then finally something a little interesting, there's two arrows. So I think about taking exactly one of these arrows. So I could take YE, but then I'm going to multiply it by every vertex on this like leg that is an instant to E. So that's x2. And then, okay, I could also take YB, but YB, and then YB is an instant to 4. So take that. So secretly I was doing that here and here, but all vertices were already instant to the arrows because it was just. And then we also have, for every consecutive pair, we have a monomial. So I have two consecutive pairs of a set of 3. So for 1, 2, I'll have x1, so everything except the kind of corner. And then there's a q there. Then for 2, 3, again, I have everything except the middle 4, so that's going to be x2 squared x3. And there's just always a q. And then here's where we record whether or not there was a relation. So here A and B went opposite directions. So this was just normal and positive, but here we pick up a negative. So unfortunately, the negative sign is necessary. Now, usually people doing cluster theory we never see negatives. This is brand new, but it's necessary for the scheme that we want. And then finally, we have something like a cross polynomial, which if you ever work with like snake graphs, we always have something like this. Here we ignore the n, so it's x2, x3, x4. So we're going to put all those all together in some way, which I'll tell you about. The way we put it together is, it's combinatorial. It relates to just like Fibonacci numbers, so really simple. So we'll call an admissible set. I guess here I'll give the general definition. A subset of the numbers 1 through n, such that its complement can be partitioned into consecutive pairs. Sorry, I should draw like these are disjoint sets. Otherwise, I guess it wouldn't really be much of a condition at all. Okay, that's an admissible set. So when n is 3, I could be all 3 numbers, or it could be 1, because 2 3 is a consecutive pair, or it could be 3 by the same logic. But it couldn't be 2, because the complement of 2 is 1, 3, and they're 2 apart. It also couldn't be the empty set, because then you'd have like an odd number of numbers left over. So this is like you should think of domino effect. Okay, so then our definition. So for this example, let's call this C of P. So in this case, so there's some Q which relates to the degree these things sit in. And so for example, if you shift your complex, this Q will just keep track of that. There's some Q here. And then we have x2, x3, x4, the cross monomial. And then we'll have things indexed by these admissible sets. So the numbers in the admissible sets, you take the like polynomials. And then when so when I had the admissible set being everything, I took all the like polynomials, multiplied them together. And here I just have I equals 1, and I take the like polynomial for 1, and then the pair monomial for 2. So this is going to be minus q x2 squared x3. All right, I'm drawing here because I don't want to do. And then for I being the set 3, now it's plus q. The 1, 2 is x1, x4. And then the like polynomial for, which is the longer. It's a little squish. Okay. So that is our new definition. Ooh, like 1 minute. Okay, that's okay. Rapid fire, say the properties it has. So for specialization, if you set q to -1, and if you set y to like some difference, so the y's correspond to arrows, if you set y to be a difference of like the head minus the tail, you recover the map to the growth indeed group. So in this case, if you there's some specialization where you would recover up to sine. Oh no, I just did. Okay, well it was P2, P1, P4, 2. there's some specialization where you would recover 2x2 minus x1 minus x. Right, keeping track of, okay, there's 2 2s and maybe like even degree and then a 1 and 4 in odd degree. Or maybe vice versa. It is also in some cases specializes to applying the normal CC map to a string module. You can kind of throw these diagrams in a way, yeah. We're still working on that, so maybe it's good I don't write it down. One cool property is that you can realize this as a determinant of a certain matrix or as a product of 2x2 matrices, which I think these things are popular with some people at the time. And this comes from the fact it's indexed by this like Fibonacci like. Apparently that we write the thing we wanted. So let me write the main theorem we have at the moment. So if gamma 1 and gamma 2 intersect, and these are arcs on the geometric model for a non-direct category that is algebra with resolution gamma 3, gamma 4, gamma 5, gamma 6. So again, these correspond to the mapping cones. Then we have CC, and if PI means the object corresponding to gamma I, we get our calculation. We get one Q inverse here, but that's again not really surprising because when you think about the pair of morphisms you get, one of them you shift the degree. So okay, I'll stop there. Thank you so much.
So Esther, so we have gentle algebras, we have the CC map on the modules on gentle algebras, and then we output some polynomials.
For normal like normal CC.
Normal CC. This is not.
No, this is quite different. I mean, there's minus signs.
So this, okay, this has nothing to do with the normal CC.
Oh, so like, okay, you can. Okay, like this picture. Okay, if I did something like this. And then, okay, I said, you can do something where this looks like the CC map, except the signs are still an issue. But if you can make some Jacobian algebra from these unfolded diagrams, add a bunch of triangles everywhere. And then you label these extra vertices with our y variables. So what 1, 2 was A, so label this YA. I mean, okay, this is maybe a conjecture, we have not finished proof. The CC map applied to like this sort of expanded with a bunch of triangles.
The usual one.
The usual one. And okay, you have to ignore signs though. So somehow you have to, if you take the signs out, then the CC map, normal CC map here would match that. Yeah, so if you have like an alternating homotopy string so that you have no relations, then it'll be a CC map to something else. A normal CC map.
And what is the cluster? Do you know?
Yeah, we don't, I mean, we like, I think if it's type A, you just get a normal cluster algebra. If you take a one loop quiver, you get Chevy polynomials. Yeah, we still want to like calculate what algebras we get. Understand that. That's a goal.
Any other, can you also get freezes from your CSC?
I was just thinking of, I mean, yeah, we should be able to label the, I guess the cubes, maybe like cube pieces, but we should be able to label the air quicker with something, you know, like a freeze.
If Q is a root of unity, can you use this to say something about the center of the scale algebra? Like,
That's a really good question that I have no idea if I answer one. You should look at, we'll look at that.
Another question. Then we raise